What if I told you there's this massive secret, a secret hiding right at the heart of quantum physics? We're talking about a story that's been buried for decades, packed with debates so deep that, get this, a lot of physicists today don't even know the full picture. So let's dig it up. Just listen to this quote. It's from an astrophysicist, someone with a PhD, after hearing a lecture on something called Bell's theorem. His first reaction was, I've never heard of any of this. Why didn't they tell me? And you know what? He's not the only one. It points to this really strange history where some of the most fundamental ideas in physics weren't just kind of misunderstood. They were basically ignored. So yeah, this isn't some accident. It turns out it's a symptom of a scientific culture that for a really long time was way more focused on how do we get the right numbers instead of asking, but what's really going on here? And that just raises this massive question, right? If even the experts were missing part of the story, what have we all been missing out on? Well, let's start uncovering some of these pieces. And we're going to start with one of the most famous names in all of science. All right, first up, Einstein's real objection. Okay, so the big myth is that Einstein's #1 problem with quantum theory was randomness. We've all heard it, right? God does not play dice. It's like the official soundbite for his entire objection. But here's the thing. That's maybe half the story. And honestly, it's not even the most interesting half. Because look at the full quote. He said, God plays dice and uses telepathic methods. Telepathic methods. I mean, wow. That's the part everyone leaves out, and it's the key. This points to what really bothered him, an idea he called spooky action at a distance. Today, physicists just call it non-locality. So what is non-locality? It's this wild, frankly bizarre idea that two particles can be connected, linked, no matter how far apart they are. We're talking opposite sides of the universe. And if you measure one, it can instantaneously affect the other one. No signal travels between them, nothing. Just poof, an instant influence. That's the part Einstein just could not swallow. Okay, so to really get why this spookiness was such a deal breaker for him, we have to back up a little and talk about the difference between a theory and, well, a recipe. You see, for decades, the standard way of doing quantum mechanics, what's called the Copenhagen interpretation, was much more of a recipe than a real theory. I mean, it's an amazing recipe. It tells you exactly how to predict the numbers you'll see in an experiment. But a true theory? A theory is supposed to describe reality. And this recipe was totally silent on what was actually going on. The attitude was pretty much shut up and calculate. And for a long, long time, that's exactly what people did. And this is where it gets really weird. The standard quantum recipe has this clunky two-step process. Step 1, a particle's potential, its wave function, just evolves smoothly, predictably, everything's great. But then step 2, the instant a measurement happens, whatever that means, the whole thing just suddenly collapses instantly and randomly into one single reality. The big glaring problem? No one could ever really define what a measurement was that made this magical collapse happen. So this awkward two-step dance, it's actually hiding a huge contradiction in our basic assumptions about the universe. It leads us to what's called the Great Quantum Trilemma. Basically, there are 3 ideas that all seem perfectly reasonable, totally common sense. The only catch, you can't have all 3. At least one of them has to be wrong. Okay, so what are they? Principle 1. The wave function tells you everything there is to know about reality. It's the whole story. Principle 2, that wave function always evolves nice and smoothly, according to one single rule, the Schrödinger equation, no exceptions. And principle 3, when you do an experiment, you get one result, not a smear of possibilities, but one definite outcome. They all sound pretty solid, right? Well, sorry, you can't have them all. And this is how the different real theories of quantum mechanics try to solve this trilemma. They each make a really radical choice. You have Bohmian mechanics, which says, nope, the wave function isn't the complete story. Then there are collapse theories, which say actually that smooth evolution rule gets broken sometimes. And then, of course, there's many worlds, which makes the most mind-bending choice of all. It gives up on single outcomes. It says every possibility happens, just in different universes. Each one has to throw out one of those common sense ideas to stay consistent. Okay, but while all these physicists were arguing about which principle to ditch, this guy named John Bell comes along, and he ends up proving something absolutely mind-blowing about that spooky action that Einstein hated so much. It turns out non-locality is a fact. So Bell basically asked the question that was eating at Einstein. Can we get rid of this spooky action at a distance and still explain the universe we see? Is there any way to make a local theory work? And here was his genius. He came up with a mathematical test. He proved, on paper, that if the universe is local, no spooky stuff, then there's a hard limit, a mathematical speed limit on how connected or correlated two distant particles can be. He basically drew a line in the sand and said a non-spooky universe cannot cross this line. And then came the kicker. The standard quantum recipe, the one that's been so unbelievably accurate at predicting things, predicted correlations that didn't just cross Bell's line, it completely blew past it. The math itself was screaming that our universe had to be spooky. Now, this wasn't just some argument on a blackboard. For decades, physicists have run the experiments to test this. And the results? They are absolutely overwhelming. Over 99% of them confirm the predictions of quantum mechanics. They violate Bell's limit every single time. It's official. Our universe is spooky. So the verdict is in. Non-locality isn't some bug in a half-baked theory. It's a proven feature of reality itself. In a weird way, John Bell proved Einstein was right to be worried. The theory did rely on those telepathic methods. But he also proved Einstein was wrong to think it couldn't be true. The spooky action is real. And that just leaves us with this huge, lingering question, doesn't it? If something as wild and counterintuitive as spooky action is a fact of our universe, what else about the very nature of reality have we fundamentally misunderstood?